My real pleasure. I'm truly delighted to be chairing this session with the talk of this year's Sigmetrics Achievement Award, my good colleague and friend Srikant. Really sharing this moment with him. So Srikant is let me say a few words of introduction, given that this is an important occasion. So Srikant is an amazing scientist and engineer with a long trail of important contributions. So Srikant did his undergraduate studies at IIT Madras and then continued with his PhD at the University of Illinois at Urbana-Champaign. After a few years at Bell Labs, he then returned to Illinois and he has been in the faculty there since 1995. Uh, 26 years, I guess time flies. So along the way, Srikant has earned many important distinctions. For example, he has received the IEEE Kobayashi Award, that's in computers and communications, an Infocom Achievement Award, Best Paper Awards at Infocom and from the Applied Probability Society of Informs. And most recently, big step up, he has become the co-director at the C3.ai Digital Transformation Institute, which is a consortium of many leading institutions with a quite ambitious agenda. Now let's get a little more technical. So from early on, Srikant did very important work related to networking. In the early days, he worked on loss models. So loss models had to do with uh, virtual circuit networks. And it was an important class of models that was quite appropriate for the technology of the time. That was in the early 90s. And with co-authors, he wrote some very important and influential papers that had significant impact on the analysis and design of virtual circuit networks. He's probably maybe even better known or more widely known for his later work on scheduling, including fair scheduling in wireless networks, where he addressed in a systematic way issues of congestion control and scheduling. So in that context, he co-authored what I find to be a beautiful monograph, The Mathematics of Internet Congestion Control, a short book, but really to the point, which I very much enjoyed reading back then, and which codified what emerged as the right way to look at problems in this space. It was a view that combined Lyapunov functions, ideas from control and optimization theory. And this line of work had its fair share of mathematics, but it was also notable because of the insights that was giving and its practical relevance. So talking about the practical side, along with this work, Srikant introduced and studied active queue management algorithms involving adaptive virtual queues. These were algorithms that were using both packet loss information as well as delay information. And these formed the basis for a protocol that was named TCP Illinois, and which actually has made it into practice in the real world. Now, besides this and many other contributions that were closely related to practice, Srikant is also notable for making major theoretical contributions that are elegant and important in their own right. So he solved a number of open problems. For example, one was about the heavy traffic behavior of input-output switches when they're operated under the max weight policy. A key ingredient here of his line of work in recent years is all about, well, not all about, but a key ingredient is to use Lyapunov functions and exploiting their drift properties, especially in contexts where one has or expects to have the state space collapse property. And so, in other words, building basically a bridge between state space collapse and the right Lyapunov functions and the right properties. And more recently, he has been using related Lyapunov techniques to study key questions on the convergence and convergence rate of reinforcement learning algorithms. But I guess I should stop here because I'm really getting into what is the title and the subject of his talk. So it's better to hear from him directly about all that. So congratulations, Srikant, and we're all looking forward to your talk.
Thank you very much, John, for that kind and generous introduction. I'm very honored and humbled to receive this award. I've had a great number of awesome collaborators, postdocs, and students, and I would like to acknowledge their contributions in all the work that John mentioned. So today I'll talk about the Lyapunov drift method. So let me share my slides and see how that works. Okay, and please feel free to interrupt me and ask me questions. So I chose the title, The Unreasonable Effectiveness of the Lyapunov Drift Method. And I'm going to give two examples, one from cloud computing and one from reinforcement learning on how the Lyapunov Drift Method can be useful. The reason I called it Unreasonable Effectiveness is that when I first was introduced to the Lyapunov Drift Method, it was in the context of nonlinear control systems and stability. I'm just amazed at how powerful this tool is, and pretty much everywhere you look, people call it different things in different fields, and sometimes people don't even call it the drift method or anything. But essentially, if you look at optimization, machine learning, and cloud computing and performance analysis, which is sort of the heart of Sigmetrics, most of the time it comes down to the Lyapunov drift method. So I'm going to give you my sort of high-level introduction into what the method is, and give you two examples of how useful it is. So there are two parts to the talk. In the first part, I'll talk about applications to data centers and cloud computing. I'm sure all of you know what these are. Of course, data centers and cloud computing are used by any major high-tech company these days, and even other companies like banks and so on. For the purpose of this talk, a data center is just simply a large number of servers or computers connected by a very large network and handling massive amounts of data. And our interest as Sigmetrics researchers is to design algorithms to allocate the resources in this network or this data center to process jobs and to characterize the delay performance of these algorithms. The second part of the talk will be about reinforcement learning. Let me select enter here. Okay. The second part of the talk will be about reinforcement learning, which again, I think most of you probably know what it is, but in a reinforcement learning setup, you have an agent or a reinforcement learning agent, which takes an action. So in the context of, for example, an autonomous driving agent, it changes the state of the system around you. So if you decide to accelerate or decelerate or brake or change lanes, it changes the relative position of your car compared to the rest of the cars in the environment. And you get feedback about the new state and also the reward that you get from taking your action. For example, the faster you go, you get a higher reward, but at the same time, you might get too close to another car, which might give you a negative reward. So there is some net reward associated with each action that you observe, and the agent then takes actions again based on this the information that you get. Of course, the key difficulty, like in the context of data centers, I said the number of servers in the network and the amount of data that it handles are very, very large. And in reinforcement learning algorithms, the challenge is that the state space can be very large. As probably many of you know, the significant successes in reinforcement learning have been in the context of playing video games or other types of games. And for example, in chess, there's something called the Shannon number, which is simply the number of positions on the chessboard, and it's roughly 10 power 120. So clearly you cannot have an algorithm that learns what to do at every position. And so somehow you have to learn to do what you do at by observing what to do at a few positions, you somehow have to generalize. And this is basically where deep neural networks or just neural networks more generally are useful. Just to make sure that we don't just think of reinforcement learning as only for playing computer games, I just thought that these papers by Mohammad Alizadeh at ICLR, NeurIPS, and one at SIGCOMM, it's kind of interesting because I think many of us in the Sigmetrics community who worked on scheduling But the kind of jobs that you see in data centers these days is very complicated. So a job could consist of many tasks. So each of these little nodes is a task. So this is one job here. So for example, this task can start if these two tasks have completed. So each job can be thought of as a directed acyclic graph where the nodes represent tasks and the arrows represent precedence relationships amongst them. And the job is completed once this last task is completed. Now we have different types of such graphs arriving to the network, and you have a large number of servers, and it's not at all obvious how to schedule such jobs on data centers such as Facebook's data center or Amazon's data center or Microsoft data center and so on. And in this paper by Mohammed Alizadeh and his co-authors, they talk about how to use reinforcement learning to learn how to schedule jobs, which are in the form of DAGs. So even though I'm not going to talk about this application, I just wanted to mention that the kind of techniques that I'm going to talk about are applicable not only for game playing, but also for the kind of problems that people in the Sigmetrics community are often interested in. Okay, so the rest of the talk, I'll give a very brief introduction to what I call the drift method, or what is called the drift method, the Lyapunov drift method. And I'm going to present two applications. In the introduction, I'm going to tell you the basic outline of the drift method. And then in the two examples, one in load balancing and reinforcement learning, I'm going to talk about how to use insight from the problem to design a good Lyapunov function to use along with the drift method. And then I'll conclude. And I think depending on the amount of time I have two open problems that I think people in this community might be interested in, and I'll mention them. Okay, so what is the Lyapunov drift method? So underneath any such method, there is a dynamical system. So you have, here's a dynamical system. W is the state of the system at time k. And the state at time k plus 1 is a function of the past and some noise, which is, by noise, I mean randomness. So for example, in the context of communication networks, queuing systems, cloud computing systems, Wk could be a vector of queue length. And the vector of queue length at time k plus 1 is, of course, a function of the vector of queue length at time k. And the randomness in the system, which is due to the arrival, this should be a slash here, arrival / departure processes in the system, so that you have a random number of jobs arriving, and then you have depending on the amount of time that it takes for a job to complete is random, and so on. Okay, so this is a stochastic dynamical system. In the context of reinforcement learning, Wk could be, for example, the parameters of a neural network. Okay, so you use the parameters of the neural network to learn something about a Markov process, and the Markov process itself can be thought of as the noise in the system. And you're changing the parameters of the neural network to learn something about the Markov process, and I'll get more precise about this later on. And hidden in this dynamical system is some control policy. For example, in the context of scheduling, the control policy, in the context of data centers, the policy could be a scheduling policy, a routing policy, and so on. So one of the early examples that I've seen is in a paper by John Tsitsiklis and Peter Marbach from the 90s, where the control policy, there's a parameter which determines the probability with which a job is accepted or not based on the state of the system. So that could be, so here theta are the parameters of the control policy. It could be a scheduling policy or a routing policy in our context, or it could be something else in the context of an autonomous driving vehicle or a chess playing computer. And associated with this dynamical system is a performance metric that you're interested in learning. So for example, we might be interested in estimating the total queue length in the system in steady state. Okay, so that could be CW of infinity. In this case, could be the total queue length in the system in steady state. Or in the context of machine learning, often people are interested in finite time performance. So you might be interested in the average value of this of some performance metric over a finite amount of time, or simply the performance metric at some time capital T, for example. So these are all, so often in the context of machine learning, people these days are most interested in knowing what happens at some finite time t, because there's a lot of interest in learning how many samples. So for example, if you want your reinforcement learning algorithm to have obtained the optimal policy or estimated something well within some time, capital T, the question might be, what should capital T be, this uppercase T be, so that you've achieved your goal. And so for that reason, finite time performance is more interesting in machine learning, whereas in the context of performance analysis for queuing systems, we often are interested in steady state performance. And what I'm going to illustrate today is that you can get both types of performance using the Lyapunov drift method. In the context of reinforcement learning, I'm not going to talk about this, but in addition to performance analysis, we may also be interested in getting an improved policy, and these are called actor-critic methods. So you start off with a policy, estimate its performance, get a new improved policy, and so on. But everything that I'm going to talk about today can be used as the basis for actor-critic methods, but I'm not going to talk about it. So what is the drift method? So basically, there is something called a Lyapunov function, which is, for the purpose of this talk, is just simply a non-negative function, L. And we study the drift of this Lyapunov function. The drift meaning the value of the Lyapunov function at time t plus 1 minus the value of the Lyapunov function at time t. And since this is a stochastic system, I'm going to look at the expected change in the Lyapunov function from one time instant to the next, given some past information. For example, the queue length at time t minus 1 or t. And if this drift of the Lyapunov function satisfies an inequality like this, so C is the performance metric of interest. Suppose I'm able to demonstrate that the expected drift is less than or equal to minus C plus some constant, then this will immediately give me an upper bound on the expected value of C in steady state. And why is that? So if you take this equation and take the expected value to remove the conditioning here, to remove this conditioning, take the expected value, and then move C to the left-hand side and move the L to the right-hand side, you get this inequality, right? And from this inequality, we are interested in estimating the steady state value of C. How do we do this? The obvious thing to observe is that the very definition of steady state means that the expected value of, if the system is in steady state, already in steady state, the expected value of L at time t should be equal to the expected value of time at time t plus 1. So in other words, this difference is equal to 0. So this inequality simply becomes expected value of C at infinity is in steady state is less than or equal to K. So a key challenge, of course, is to figure out what a good Lyapunov function is to find C. And I'll give you an example today in the context of cloud computing, where you can sort of get insight from the problem to design a good Lyapunov function. There are some technicalities that I'll ignore today. I'll keep the talk at a very high level, but I'm happy to answer any questions. As I said, the Lyapunov drift method can also be useful to find to obtain finite time bounds. It's the same type of equation. So here, instead of the additional part here being a constant, I'm allowing it to be a function of time, which turns out to be useful in the context of reinforcement learning problems. Again, I can just manipulate this equation, move the C to the left-hand side and the Lyapunov function to the right-hand side. However, it's no longer true that the expected value of L at time t is equal to the expected value of L at time t plus 1, because we are not in steady state. We are interested in finite time performance, starting from any initial condition. But nevertheless, this is a standard trick we all know, which is if you sum this equation from 0 to t minus 1, for example. So there's a telescoping happening here, and everything but the first and the last term, L at 0 and L at time t, will remain. And since there's a negative term, a negative sign in front of L at time t, you can just drop that. And so you get a average. So you can see that the average value of the performance metric of interest over t time units can be upper bounded in this manner. And since this is an initial condition, this doesn't matter too much. And basically you get an answer in terms of this. Of course, in practice, you might be interested in just the expected value of C at some time, fixed time, capital T, rather than the average over some time. And some additional work needs to be done to do that, but that can also be done, okay? So the question of interest is what Lyapunov function to choose, and that's what I will focus on using 2 examples. So are there any questions about the drift method itself? If you have any questions, as they said, I think please raise your hand or put your questions on chat. Okay. I think this is pretty simple. I mean, the reason I like the Lyapunov drift method is that it's so simple. I mean, the main trick is to figure out the right Lyapunov function, and often one can get insight into the right Lyapunov function by just studying the problem. Okay, so the first example I'm going to give is in the context of load balancing. So this is joint work with Wenta Wang, who visited me when he was a junior at Tsinghua University, and so he's part of the host institution. He will be moving to MIT soon as a graduate student. And Xingyu Zhao, who's an assistant professor at Wayne State University at the time we did the work, he was a graduate student at Ohio State University. So the problem I'm going to look at is one of load balancing with data locality. So if you think of a data center, all the servers are generating jobs for each other. So for example, here's a server that that's generating a job, which requires a green type of data. So I'm assuming that there are different pieces of data in the network. So for example, you might be searching for the occurrences of the word Joe Biden in all CNN news stories yesterday. So this job can only be executed at servers that store the CNN news stories from yesterday. So maybe if you're doing a Google search, and the Google search the search query can only be routed to the servers that have the data on which this query can be executed. So therefore, this job can be executed either at this server, which contains green jobs, or this server, which contains green jobs, but cannot be executed at this server because it does not contain green jobs. There are other models, in particular, I think this load balancing problem with locality. I first learned about it from this paper by Weina Wang. It's part of a thesis done under the advice of Lei Ying. So this is a 2014 paper, and the model they use is a bit different. So I'm going to assume the jobs can only be routed to servers that have the data. You can also have other models where you route the job to any server, and the server goes and grabs the data from some other server if it doesn't have the data itself, and that'll add to an additional delay and so on. That's this style of work here. But I'm going to use the model in these 2 papers. It originated in this beautiful paper by Mukherjee, Borst, and Dewar, which was generalized in a stability setting by Cruz, Jonquière, and Schneer. So I'm going to assume that jobs can only be routed to servers which have the data required to execute the job. And this is very useful if you're trying to achieve 0 delay, okay, in the network. So the picture that I had in the previous page can be abstracted in this manner. So you don't have to think about servers sending jobs to each other. You don't care where the jobs are coming from. So there are L types of jobs that are arriving to the to N servers, okay? And there is some connectivity from left to right. So for example, this arrow here indicates that jobs of type 1 can be processed at servers at server 2. This simply means that server 2 has the data required to execute jobs of type 1. Similarly, so jobs server N, for example, from the server side, it can process jobs of type 2 and jobs of type L. Okay, so the connectivity information just simply says which jobs can be processed at which servers. And the question of interest is, we have to come up with a policy to route jobs. For example, when a job of type 1 arrives, are you going to send it to a server 1 or server 2? Okay, so the goal is to figure out some algorithm to minimize the mean response time. And we're interested in systems which are very, very large. So we might be interested in the limit as n goes to infinity. And we might also be interested in what happens when n is not quite infinity, but for finite size systems, what is the performance? So our main results are for a well-connected system. What do I mean by a well-connected system? If there are enough edges going from left to right. In a well-connected system, join the shortest queues asymptotically optimal, meaning that for homogeneous servers. By homogeneous servers, again, what I mean is all the service rates here are mu. Okay. If the service rates are not homogeneous, then join the fastest of the shortest queues is asymptotically optimal in terms of minimizing the response time. Join the shortest queue itself doesn't work. You have to do join the fastest of the shortest queues. The join the fastest of the shortest queue is a very simple variant of join the shortest queue. So if you have two queues with the same number of jobs waiting, so in this example, both queues are empty, you would prefer to send the jobs to the faster of the two servers. Okay. Of course, you don't need to know the exact processing rate of the two servers. You just need to know which one is faster. Okay, that's very important. So you don't need to know the processing rates. You just need to know, if the one is a newer computer than the other, then of course the newer computer would be faster, and then you would send it to the newer one. You just need to know the relative rates. And so that's what I'm going to talk about in this talk. And I want to mention that there is contemporaneous work using completely different techniques. And just for the first part, for the join the shortest queue part, by Rattan and Mukherjee, and I encourage you to look at that. So they use fluid models to study the problem, whereas I just study we study the problem directly using the drift method. Okay. So I've already mentioned that we are interested in very large systems, and of course you won't have a very large system unless the arrival rates are large too, correspondingly. So I'm going to assume that the total arrival rate scales with the size of the system. Okay, and in practical system, the buffer size, or the number of jobs that can wait at each server, is finite. So I'm going to further assume that the buffer sizes are finite. So those of you who worked on mean field limits would know this. So the notation we use is that SI is a fraction of servers with at least I backlog jobs. Sorry, this should be S1. So the number of busy servers by Little's law should be equal to lambda if the departure rates are all 1. And we are interested in the total number of jobs in the system, which is just the sum of all of these. Okay, the sum of SI I greater than or equal to 1 multiplied by N is the total number of jobs in the system. And we don't want any jobs waiting in the system. So in an ideal system, by the way, the talk in today's talk, I don't know if I mentioned it, I'm going to only talk about the homogeneous server case. The heterogeneous server case is in this year's Sigmetrics program. And I encourage you to attend the talk to find out more about the heterogeneous case. So in an ideal system, we just want exactly one job waiting in every server, or no jobs. So the total number of jobs in the system should also be equal to lambda. Okay, so this is what we'd like to prove. Okay, that's the goal here. So our main results are the following. So for a well-connected system, we show that essentially there is no delay in the network, and this slide is of course too ridiculous to parse. So I'm just going to say it in words. So the key assumption is that any large subset of servers, if you consider any large subset of servers, they must be connected to a large number of sources. That's roughly what the well-connected assumption means. So here is a small subset of servers, and these may not be connected to every arriving job. I mean, so to a lot of the sources. But if you consider a large subset of servers, then they must be connected to a large subset of sources. So this is the well-connectedness assumption. Under this assumption, we show that in the homogeneous case, join the shortest queue is asymptotically optimal. Asymptotically goes to 1, meaning that the delay asymptotically goes to 1. And the blocking probability, because I used a finite buffer size, the blocking probability goes to 0. And for finite sized systems, the delay is not 1 and the blocking probability is not 0, but the actual numbers, we have expressions for it, which I had on the previous slide. And the actual expressions depend on the buffer size, the connectivity of the graph, and the size of the system, and so on. Okay. Okay. So I've already mentioned this. So SI is a fraction of servers with queue length greater than or equal to I. And what we would like to show is that S1 goes to lambda, and the number of queues with greater than or equal to 2 jobs waiting is greater than or equal to 1 job. Sorry, this should be greater than 2 jobs waiting. It goes to 0. Okay, and this is true for classical classical load balancing in join the shortest queue. We want to show a similar result for our bipartite graph load balancing problem. So the metric of interest is that I want to show that the total number of jobs in the system is equal to lambda. So ignore the epsilons and deltas in the top. We need that for proof purposes. So essentially, I need to show that the total number of jobs in the system is equal to lambda. So this is my performance metric of interest. And often, you just take the square of that performance metric as the Lyapunov function. So in this particular case, apply the drift method. The Lyapunov function that you have to choose is very easy. However, as you go through the analysis, at some point you have to show the system is not in this state, but is most often in this state. And for this reason, you need a second Lyapunov function, and you have to apply the Lyapunov drift method a second time. And this is sort of a feature of many of the problems that I've worked on in the heavy traffic analysis that John mentioned on switch scheduling. A similar thing arises. Basically, so the system is not in the state on the left. What does that mean? If there are many jobs in the system, they should not all be piled up on one server. Okay, they should be distributed everywhere so that all the servers can be used. This is obviously true for join the shortest queue. Now, I don't have a simple join the shortest queue system. Sorry, what I mean is, if for parallel server systems, when a job can be sent to any queue, then this is reasonable. But if the job cannot be sent to any queue, but they're constrained by this connectivity in the bipartite graph, then is this true? And I think this is somewhat related to this paper by Kwang Shu and John on how much flexibility is needed in load balancing systems. So for this particular problem, this is a beautiful Lyapunov function that Lei Ying and Xin Liu came up with, which is useful to show that this happens, the situation on the right happens. And it's sort of intuitive to see the Lyapunov function in the form of a picture. They did it for something like join the shortest queue with limited flexibility, but I'm using it for the bipartite load balancing problem here. So the Lyapunov function consists of two parts. One part is basically the purple shaded picture here, which is simply the total number of servers with greater than or equal to 2 jobs in the system. And the other part of the Lyapunov function tries to capture the number of empty servers in the system. So if VS is small, basically one of two things must be true. The number of empty servers is either small, or the number of servers with significant backlogs is small. So if you study the Lyapunov drift of this function, then you can use that to show that VS itself is small in some appropriate stochastic sense. Okay, and so therefore the flip side of it is, when VS is large, you should show that it decreases very quickly. And what does VS being large mean? Because VS is a minimum of 2 quantities, so both of these terms must be large, which means the number of idle servers must be large, and the number of servers with 2 or more jobs must be large. And this immediately implies that V must be negative. And this is where the crucial assumption that I mentioned, that the system is well connected, matters. Because if the system is well connected, and if there are lots of empty servers, that means that since the number of servers is large, as I said, if you have a subset, if you consider any subset of servers with a large number of servers in them, then they're connected to enough number of sources, so load balancing is possible. So all of these sources will try to avoid these servers with enough jobs, and they'll pump all their packets here so that the system will move to the state, which in this cleverly chosen Lyapunov function that Xin and Lei came up with, automatically means that the drift of that Lyapunov function is negative. So this is the basic idea. So this is a high-level talk. I'm not getting into the details. So putting it all together, so we have 2 Lyapunov functions. One to produce the performance metric of interest in the Lyapunov drift inequality that I mentioned, and the second Lyapunov function, which is useful in intermediate analysis. And putting them together, we can show that join the shortest queue is indeed optimal for the homogeneous server case. So the analysis of join the fastest of the shortest queues is a bit more complicated, and that will be in the Sigmetrics program on Thursday if you're interested. But the key ideas presented here are essentially the same. Okay? There's no fundamentally new ideas in the join the fastest of the shortest queue case either. Okay, so the next part of the talk is on neural TD learning. And I'm going to consider a very simple reinforcement learning problem here. And this is joint work with my postdoc, Semi Chechi, who's absolutely brilliant guy, and my current student, Siddharth Satpathy, who will be graduating soon, and Niao He, who used to be my colleague at Illinois, and she recently moved to ETH Zurich, and she's a professor of computer science there. Okay, so I'm considering a very simple reinforcement learning problem. So I have a Markov process whose transition probabilities are unknown, and there is something called a value function associated with each state of the Markov process. What is the value function? The value function is the sum of rewards starting at state Y. So if you start at state Y, and each time you transition to a new state, you get a reward. And the value function is simply the sum of the rewards discounted by a discount factor, gamma. Okay? And we need to learn the value function by observing the states and the rewards. Okay, so you just you get, for example, in the context of a self-driving car, you've driven your car for a long time. You observed at each time instant what your relative position of your car, maybe that's the state of your system with respect to the other cars, and there is a reward which basically is a function of how fast you're going and how close you are to other cars and so on. So you've observed all of this over some time, and basically you have some policy. You have autonomous driving agent is executing some policy to drive the car, and you want to understand how well this policy is working. Of course, this is one step in reinforcement learning. The next step is, of course, you want to refine this policy or improve this policy. I'm not going to talk about that today. I'm just going to simply talk about the question, discuss the question of how to estimate this value function for each state of the system. Of course, this is impossible to do because the number of states is huge, typically, and sometimes even uncountably infinite, and we observe only a finite number of samples. So what can we do? So we approximate the value function using a neural network. So if you're not familiar with a neural network is just a linear combination. For the purpose of this talk, it is just simply a linear combination of nonlinearities. So AI are the parameters of the linear combination, and the input x, the state of the system, is multiplied by some w, which is a vector. So wi transpose x is a scalar, and so wi transpose x plus is basically only allowing you to pass the positive side of wi transpose x. So this is a very well-known neuron. So this a neuron is just simply a nonlinearity. This is perhaps the most widely used form of a neural network, and this is called this particular neuron is called the rectified linear unit, which is just simply just a plus sign. So if you give it a 5, then the output will be a 5. But if you give it a -4 as input, the output will be 0. So I'm going to approximate my value function using a neural network where m is the number of neurons. As I mentioned, x, the input, could be very large dimensional or even infinite dimensional. But I'm going to approximate that using a neural network with a finite number of parameters. In deep reinforcement learning, everything that I'm talking about can be extended to deep reinforcement learning as well. But there you'll have multiple such layers. So this is called what is called a single hidden layer neural network. You could have multiple hidden layers, and then it would be called a deep neural network. Okay. So I want to figure out what the I'm observing the x's and the r's, and based on these observations, I need to choose the AI and the WI to well approximate the value function. So this is the problem. So the algorithm we are going to use is one that was suggested by Sutton. I think this should be 1988. And basically it is motivated by the so-called Bellman equation. So the value function in state X is simply the immediate reward plus the long-term reward, which is just value function from the next state multiplied by gamma. So it is well known that the value function must satisfy the Bellman equation. So Sutton's suggestion was, why not? So we don't know this expectation, so I'll remove the expectation and look at the difference between the right-hand side of this of the Bellman equation and the left-hand side of this Bellman equation. And we'll adjust the weights of the neural network in proportion to this difference multiplied by the gradient of the value function with respect to the unknown parameter. So this is somewhat like gradient descent, but it's not quite gradient descent for reasons I'm not going to get into here. Okay, it's not exactly gradient descent, but it's sort of like gradient descent. Okay, And we want to know if this algorithm converges those set of parameters for the neural network which approximate the value function very well. And in addition to the basic Sutton algorithm, I'm going to use some sort of projection to make sure W doesn't stray from W0. So there's some initial, so you initialize W at some W0, and you want to make sure that W does not stray very far from W0. And there are two ways to do it. One is called early stopping in the machine learning literature. It just simply means that to get some desired error, we're going to run the algorithm for a certain number of samples. Okay, so you stop it at WT, in which case you'll know that whatever value you got, you did not drift too far away from W0. And the second one is a more natural projection, which we are familiar with. So each parameter vector of the neural network, I'm going to make sure it doesn't stray too far away from its initial condition. Okay, so I'm using projection to control how the the parameters of the neural network evolve. If you recall, there were two parameters in the neural network. Let me go back here, A and W. For the purpose of this talk, I'm going to assume only the W's are learned. I'm going to randomly choose the A's and fix them. And the W's are initialized according to some Gaussian distribution. The AIs are initialized according to a Rademacher set of random variables. And I'm going to fix the A's, whereas W's I'm going to change. And I'm initializing the neural network in what is called a symmetric fashion. So I initialize half of them, and the remaining half are essentially chosen based on the first half. And this will be useful for analysis. You can also do this without symmetric initialization, but the symmetric initialization makes it easy to do the analysis. So the question of interest is, so suppose I give you an approximation error epsilon. How many samples and how many neurons do I need to get my approximation error? So V hat is the estimate of the neural network, estimate of the value function after capital T time units, and V is the true value function. And I want to make sure that the difference between these two is less than epsilon. And the seminal work in this area is by Tsitsiklis and Van Roy from 1997, where they showed that this algorithm that I mentioned converges with linear function approximation. Not nonlinear function approximation like a neural network is, but assuming the function approximation that you're choosing, V hat, is a linear function of W, not a nonlinear function of a linear function of both X and W, both the input and the parameters. Here is nonlinear in both. Okay, so there is also other work on neural TD learning, the same topic that I'm talking about, by Kai, Yang, Li, and Wang, and the analysis there is related, but we are doing something quite different, and their analysis builds upon the work of Jacot, Du, and the first keynote speaker, Sanjeev Arora, in the context of classification and regression. Our work builds upon the work of G and Telgarsky. Matus Telgarsky is my colleague here in computer science on studying classification and regression problems. So basically, I would say that our analysis is sort of a combination of these two works, Tsitsiklis and Van Roy, and G and Telgarsky.
So Srikant,
yeah.
There's a question. So let's.
Okay.
Okay. So.
Is it in chat, or is it the person raised their hand? I can't see chat. Oh, sorry, I can't.
So it's Luis. Can you answer ask your question?
So sorry, I do not have a question.
Oh, you didn't have a question. Okay, okay. So it was an accidental hand raise. Okay, so my the analysis in our paper is a combination of these two ideas. So the high level intuition is this. So I said V is a function of the state, and the state could be uncountably infinite even. How can you possibly estimate it based on a few samples? So you have to assume that V is smooth, and you can look at it in the paper. For those of you familiar with reproducing kernel Hilbert spaces, you can. So the way we characterize the smoothness of V is in terms of the RK. So we assume that the value function lies in a reproducing kernel Hilbert space, and we assume that the norm of the value function in the RKHS norm of the value function is bounded. And we also assume that X is a compact set. then we can focus on estimating. If you have enough samples, then we can estimate V at those states that you observe reasonably well. And since the function V is small, it won't vary too much at the other places. And so you've got a good estimate everywhere on the compact set. This is the basic idea. I mean, I'm oversimplifying everything, but that's the basic idea. And the question is to figure out how many samples do you need to do this, okay? And how many neurons do you need in your neural network? So these are the two questions of interest. And I'm going to tell you how to do this, how to estimate this by finding the right Lyapunov function. So one key difference between regression and classification and Markov decision processes and reinforcement learning is that in regression and classification, which I think probably will be in Sanjeev Arora's talk, so you observe a particular image, for example. So instead of states, you have in classification problems, you're given images of cats and dogs. And for each image, you're told if it's a cat or a dog. So you're told if it's a +1 or a -1. So a cat could be +1, a dog could be -1. So you're given a bunch of labeled images, and you're trying to learn the connection between the labeling and the images, okay? In reinforcement learning problem, I need to find a connection between the state and the value function, but the value function is not given to me. I only observe some instantaneous reward, whereas the value function is a long-term sum of these rewards. And in addition, the xi's are not IID. So what we have is a Markov chain, although I'm not going to, in this particular paper, we sort of made an IID assumption, but it can be relaxed using a sort of ideas in a cold paper that I had with Lei from 2019. So only some of the intuition from regression and classification applies. So it has to be sort of a judicious combination of using insight from regression and classification and sort of the ideas, for example, from the Tsitsiklis and Van Roy paper. So what is the basic idea? To apply the ideas from the Tsitsiklis and Van Roy paper, one has to linearize the neural network somehow, okay? So I have a function. The neural network has a nonlinearity of this form. And what is the derivative of this? Of course, it's not differentiable at y equal to 0, but everywhere else, the derivative is indicator y greater than or equal to 0, right? So I'm just going to pretend that it's not differentiable at origin. I'm going to ignore that. Of course, I mean, that'll all be taken care of in the proofs carefully. So we just linearize the neural network around the initialization W0. So if you linearize, so to linearize, you need to compute the gradient, and then you use this formula to compute the gradient, okay? And then now you use Taylor series and just retain the first order term. So these ideas, so as I said, there's a combination of ideas from these ideas that are used in classification and regression problems. And if you do that, then the neural network can be approximated like this. And the whole idea of adding making sure that you're doing a projection is to make sure that the initial condition does not stray too far from the parameters of the neural network don't stray too far from the initial condition, so that this linearization is approximately correct. So that's the basic idea. There will be a 0th order term here normally, but our symmetric initialization actually got rid of this. And now this is a linear problem, just like the Tsitsiklis and Van Roy paper. So the idea is that hopefully we can use the analysis, combine the basic idea behind the analysis in the regression and classification problems for neural networks, where they sort of justify how this linearization can be handled. And the Tsitsiklis and Van Roy paper, which assumes that everything is linear. So basically you put the two things together, and of course, it's not as easy as I say. This pesky approximation here has to be justified, and it's definitely non-trivial, but that is the basic idea. So what is the Lyapunov function that one needs to choose? So let's look at Sutton's algorithm. Sutton's algorithm suggests that WT plus 1 is chosen as a function of WT plus something, which is what's called the Bellman error multiplied by the gradient. So essentially WT minus W0 is just simply a linear combination of the gradients at various time instants, okay? And what are the gradients at various time instants? So since this is a linear function, the gradient term will be very, very simple. And so it's very easy to show that the function will stay within this linear class like in the Tsitsiklis and Van Roy paper, as long as W doesn't stray too far from W0. So basically our assumption is that, not our assumption, so I guess it's our assumption. So I said earlier that the value function lies within a certain reproducing kernel Hilbert space. So I did not want to get into RKHS in this talk, but the basic idea is that I'm going to effectively, my assumption is that when the number of neurons goes to infinity, this linearization approximation leads to a rich class of functions. And the rich class of functions can be represented by this thing called the reproducing kernel Hilbert space. And I'm assuming that the value function lies within this reproducing kernel Hilbert space. But what does it mean in simpler terms? In simpler terms, I mean that there's a Tsitsiklis Van Roy kind of linear approximation that we are assuming. And the weight vector, suppose there's a weight vector W star, which is the true weight vector or or this is the weight vector to which the Tsitsiklis Van Roy algorithm would converge. Okay, and we are going to basically use our Lyapunov function to be WT minus W star. If anybody who's done control theory or any class, so the natural Lyapunov function to use is basically if you expect WT to converge to W star, you take WT minus W star squared to be the Lyapunov function. And so the rest of the analysis is sort of somewhat complicated and cumbersome, but basically the idea is you pretend that if you pretend that your function approximation is linear, then you can appeal to the Tsitsiklis and Van Roy paper. But since it's not linear, then you appeal to this huge body of work in the neural network literature called the neural tangent kernel. And basically combining these two produces our main result. The main result, so we have multiple results in the paper. I'm going to sort of contrast two algorithms. So one algorithm is the projection-free algorithm. So you don't use any projection, but you stop the algorithm after some capital T time units. So if you stop the algorithm at an appropriate place without using projection, then you need overparameterization. So the number of samples you need is of the order of 1 over epsilon power 6, but the overparameterization. So you need roughly as many neurons as well. Okay. On the other hand, if you do the projection that I mentioned, then you can show that the number of neurons that you need is actually smaller than the number of samples you need. And so you might have heard of this term called overparameterization in neural network literature, and you don't need that for this problem. So you can have the number of parameters that you have need not be as much as the number of samples that you have. And this parameter nu bar that I have here is sort of, it is the norm of the value function in the reproducing kernel Hilbert space. So our main result is that the expected value of the difference between V hat and V is small on almost all sample paths. Okay, so that is the main result. So basically I've come to the end of my talk. I just want to end with 2 slides. For those of you interested, there are 2 open problems in the two talks that in the 2 parts of the talk. The first part of the talk, I assume that each server, the average time that jobs of all types take at each server is the same. So I called this mu1 in my talk earlier, but it's more interesting and realistic if different jobs take different amounts of time at the server. Okay, and for this problem, we don't know whether join the fastest of the shortest queues is optimal or not. So this is an interesting open problem for those of you looking for open problems. And in the second part of the talk, analysis can be extended to deep neural networks, but that's not very interesting. You have to really show that depth actually helps in some manner, right? I mean, deep neural networks are known to work better. And right now we have some interesting results. So our main interesting result here is that the use of this particular type of projection actually helps in reducing the complexity of the neural network that is used. So we believe that using more layers in the neural network would further reduce the number of neurons that you need, but this is something we haven't been able to show. So this is the end of my talk. So I love the Lyapunov drift method, and I gave you 2 examples of its applications. And part of the reason I called it the unreasonable effectiveness is that it's actually useful in a wide variety of areas. Originally, I was planning to have like 1 or 2 slides on multiple things, but then I thought, I wasn't able to figure out how to do that. So I wanted to mention there's a bunch of other things that one can do with Lyapunov drift analysis. Of course, it originated in stability analysis. and utility-based resource allocation, which is actually being used in online learning these days. The exponential moment bounds are also very interesting, originated by Hayek and later by Bertsimas, Gamarnik, and Tsitsiklis. Exploiting state space collapse. Sivateja, I've worked with this with Attila and Sivateja and a number of other people, but I think Sivateja is continuing to work on this, is getting more beautiful results. And it's also useful in reinforcement learning in actor-critic type algorithms. So this recent paper by Agarwal, Kakade, Lee, and Mahajan is a nice introduction to understanding how the Lyapunov drift. They don't call it that, but basically the paper is about using the Lyapunov drift method for choosing by using an appropriate Lyapunov function to study what are called natural policy gradient methods, which is a type of actor-critic algorithm. So that's it. That's the end of my talk. Thank you.
Thank you, Srikant. That was a wonderful talk. Let's see, do we have any questions? So if you have a question, please raise your hands or type something in the chat. Okay, Vijay, please go ahead.
Thanks, John. Yeah. Hi, Srikant. Thanks for, sorry, my video is off. But, thanks for an excellent talk again. I had two questions, which was mostly on the Lyapunov method. One was seems to need distributional assumption, but that may not be known in practice, or there may be uncertainty in a class of distributions. Can it extend to that, or how would you think?
Sorry, say that again. I didn't quite understand. What do you mean by that?
I mean, there are strong assumptions being made, either it's exponential or there's underlying Gaussian. If there was some uncertainty in the distribution, how would these methods extend? And the second one is related to time homogeneity. And so we have most of what you presented was a time homogeneous Markov chain. But suppose it was an online problem and it was not time homogeneous, how would the methods extend?
Right. So let me answer the question for the two parts separately. So in the steady state analysis part, I make two assumptions. One is that the stationary distribution exists, and the expected value of the Lyapunov function under the stationary distribution must be finite. So if the Lyapunov function, for example, is a second moment, then you must have second moments. Other than that, there are no other assumptions. So we just need those two assumptions for the first part. Now, for the second part of the talk, when you're interested in finite time bounds, you don't need time homogeneity. So you do not need time homogeneity. So in fact, in the drift method, the expected value of the drift can be negative plus something. That something can actually depend on time. So which is exactly what happens in this in the TD learning problem that I mentioned. It is indeed true that it's a think. So the underlying Markov process, I'm assuming, is time homogeneous. Does it matter? I'm not sure. I think as long as you can just exhibit this drift property for finite time analysis, I don't believe that time homogeneity is needed, but I have to think about it a little bit more. That's a good question. And regarding uncertainty in the probability distribution, I guess so I have some recent work where we deal with distributional shift in the Markov process, basically using the theory of risk-sensitive exponential cost problems. So there's a long history in control theory connecting robust control and exponential cost problems. And there, basically, what you're saying is that if instead of using the expected long-term average cost, if you use expected value e raised to the power of the cost, then basically your answer will be robust to distributional shift in the probability transition matrices. And the distributional shift is characterized in terms of KL distance between your between what you think is the probability transition matrix and what the true probability transition matrix is. So there's some way to handle that, but then the exponential cost risk sensitive problem is quite difficult to handle because of the product form of the Bellman equation rather than the additive form. And so there are some approximations that people like Shai Manor, Marco Pavone, and other people have worked on. But I'm very interested in figuring it out for the exponential cost because it's a much more challenging problem. So we do have a result on that, but there's more work to be done. So the variance of the estimates would be large and so on, and I'm still thinking about it. So I hope I answered your questions a little bit.
No, you did. Thank you. Yeah.
I don't see any other questions.
So I guess there is one question
Just came in the chat.
Yeah, a general question. I wonder if there are any connections to be made from your perspective between potential functions potential functions are Lyapunov functions. So my long time ago, my PhD was in the control theory area, and we call them Lyapunov functions. I guess often in computer science, people call them potential functions. I guess in game theory, people use the term potential function. I call it Lyapunov function because it just that's what I was taught. Yeah. And I used to call the parameter in optimization algorithm step size, and now it's cooler to call it learning rate. So I just still use old terms. Yeah, it is Lyapunov function is the same as the potential function, and it is widely applicable, not just in the context that I mentioned. I mean, it's used in online learning, it's used in game theory, it's used everywhere. Yeah. Thanks for the question.
So I think we are pretty much at the end of the allocated time slot. So I guess I just would like to thank you for your great talk and congratulations again on this very highly deserved honor.
Thank you very much, John. Thank you.
So the program indicates that there's a short break now.
Yes. So thanks a lot, Srikant and Professor Dixicus for hosting the World Achievement World Talk. So we're going to have a 15-minute break, and the keynote is going to start at 10:45.
Thank you.
Thank you all.